All right. So, from when you're talking about magnetism and electromagnetism, it's all about combining electricity with what magnetism to produce what electromagnetism. So, for this scenario, assuming that this one is a conductor, so let's take this one as a conductor. Okay. The moment there's a current that has been passed through this conductor, there's a magnetic field that will be produced, okay, along this conductor. So that is what it has been illustrated here. And based on the direction of the current, you are either going to get the magnetic field lines coming out of the page or inside the page. So when you see something like this, when you are solving a question, or when you see a question and you see something like a plane and you are seeing these cross lines, it means that the magnetic field is what? Into the plane, it is inward. And when you see the dots, it means that the magnetic field is what? Outward. So when we are talking about velocity vector, this is a typical diagram for velocity vector, where this one is our source. Okay, this one is our source of charge. It has been connected to a voltage, and this one is the magnetic field lines. So here we are seeing cross, indicating that the magnetic field is inward. So the moment the velocity vector has been turned on, it produces positive charges, and these positive charges passes through this selector up to this side. So this is the direction of the velocity, and that's what I'm trying to say. This is the direction of the velocity, and here the charge, the source of electricity is providing the magnetic field lines. So from here we can derive an equation that velocity is equal to electric field divided by the magnetic field. So the magnetic field produces magnetic force that is produced by the electric field. So at the end of the day, we can generate a formula that Fe, which is the electric force, is equal to magnetic force, which is Fb. So from our previous lessons, our Fb, which is the magnetic force, is equal to the charge times the velocity times the magnitude of the magnetic field lines, sine theta. So if our theta is equal to 90, then sine 90 is 1. Okay, so here we are going to get a general equation to Fb is equal to QVB. Okay, because the sine theta is 1, so we are not going to include any sine theta again. But we are having our electric force. Now electric force is equal to QE. Okay, our electric force is equal to QE. So from this equation that our electric force is equal to magnetic force, then we can equate the two. So our QVB is equal to QE. We are having charge on both sides, so the charges can cancel out. This means that the charges are not important in the equation for velocity of a particle passing through a magnetic field. So from here we can just make an analysis that VB is equal to electric field. If you want to find velocity, then our velocity will be equal to electric field lines divided by the okay. So the same thing applies to mass spectrometer. For mass spectrometer, the particle moves in a circular motion. So if it moves in a circular motion, then this means that there is a force called centripetal force, and it's the one that provides a magnetic field. So if that's the case, then our centripetal force is equal to our magnetic force. So from here we can equate the two equations. This is the formula for centripetal force. mv squared over r is equal to qvb. We are having a velocity here, we are having a velocity here, so one can cancel the other. So this velocity is going to cancel the square, and we are going to get mv over r is equal to q times the magnetic field. And when we are asked to calculate the radius of the mass spectrometer, the radius of the mass spectrometer is just obtained by making r the subject. So r is equal to mass times velocity divided by the charge times the magnetic field, which is the b. So now let's move on. They said that note, when you are using the hand rule, there are some things you should know. When you are using the hand rule, depending on the type of the charge you are dealing with, if it is a positive charge, you have to use your right hand, and if it's a negative charge, you have to use your left hand. So in relation to the magnetic field, the velocity and the force itself, they are all at right angle to each other. All the three components are at right angle to each other. For instance, if you are having your magnetic field lines here, you'll be getting your velocity to be in this direction. which is perpendicular, the same thing applies to the force. So at the end of the day, one is in the x direction, the other one is in the y direction, and the other one is also in the what? The z direction, which is a 3D dimension analysis. So now, hope you all understand the summary of the introduction to magnetism. Now let's go to the electromagnetism induction itself. So when you're talking about electromagnetism induction, there are some laws that you should keep in mind, which is the Faraday's law and the Lenz's law. The Faraday's law is just talking about how an EMF will be induced whenever there's a magnet that has been passed through a coil. Okay, that's all about Faraday's law. So from Faraday's law, provided we are having a loop of wire, if you are having this loop of wire, the moment this magnetic force bar is inserted into the loop of wire, there will be an EMF that will be generated. Okay, there will be a temporal EMF that will be generated. So when the magnet is inserted into the solenoid, or let's say the wire loop, an EMF will be induced, which will act as a temporal source of energy. Okay, but there is one contradiction that you should know, that when this EMF is produced, it will tend to produce a current which will act in opposite to the source of the magnetic field. And that's what I'm trying to say. So here, hence the Faraday's law is all about induced EMF, and there can be an equation that could be generated from it, that the induced EMF, which is the E, is equal to the negative the negative change in the magnetic flux divided by the time, or the change in time. So there's one thing you should keep in mind: the moment there's a change in flux, which is a magnetic flux specifically, then this means that we are supposed to get an EMF. An EMF will be induced. But when you are having a flux, but the flux is not changing, then this means that there will be no EMF that will be induced. Okay, that's why they say change in magnetic field divided by the change in time. And that's what I'm trying to say. When you are having the initial magnetic flux to be equal to the final magnetic flux, then this means that there is no change in the magnetic flux. For that matter, there will be no EMF that will be induced. And the negative sign that is there is actually there to represent Lenz's law, indicating that the EMF acts in opposite direction to the change in the magnetic flux. That is generating the same EMF. Okay, so from Faraday's Lenz's law, from Faraday's Lenz's law, we can induce our E, which is the EMF, is equal to the change in magnetic flux divided by the change in time. When the number of loop is more than 1, then we have to bring an N. This N indicates the number of loops of the wire. Okay, when you are having this general formula, then this means that the number of loop is 1. But the general formula for the EMF is negative N change in magnetic flux divided by the change in time, where the N is the number of loops. That one you should keep in mind. Now there are some observations that I want you to know. Now, when you are having, let's take a resistor for instance. This is a connecting wire, this is a resistor, and this is another point B. This one is point A. The current is flowing in this direction. As you can all see, the current is flowing in this direction. If the current is flowing in this direction, then it means that the potential at point A, is greater than the potential at point B. And the reason why it is so, because resistor tends to oppose the flow of electric current that passes through it. So at the initial stage, before the current passes through the resistor, there were many currents, but because the resistor opposes the flow of current, before at point B, the number of currents that will be at point B will be lesser than the number of currents at point A. Okay, that's for resistors. So this is the direction of the current. So for that matter, our VAB is equal to IR. The IR is the same thing as potential from Ohm's law. Ohm's law is equal to the current times the resistance, which is greater than 0. So this means that potential at A minus potential at B will still give you a number which is greater than 0. I mean a positive number per se. Now, this was just to help you understand some terms here. Now let's move on to a loop of wire or an inductor, for instance, which sometimes we refer to as mutual inductance mutual inductance. So at this point, the same thing also applies. When there's a current here, as I said earlier, when you're having a loop of wire and a magnetic field is passed through it, or there's a current that has been passing through it, then definitely there is going to be what? A flux that will be produced. But when the current is constant, look at this side, the current is constant. It has been indicated that the current is constant. So this means that what? The change in what? I divided by the change in T is equal to 0. And when the current is constant, the flux, the magnetic flux that will be produced will also be constant. And from Faraday's law that I was stated earlier, when the magnetic flux is constant or the magnetic flux is not changing, there will be no induced EMF. For that matter, VAB, which is the potential at A and potential at B, will be the same, which is the potential at A minus potential at B will still give you 0 because there is no change in magnetic flux. So these are the things that you are supposed to keep in mind. Now let's jump into some situations where we are going to get the current either increasing or decreasing. Now, when the current is increasing, this means that when the current is increasing, this means that at this point in time, potential at A will be greater than potential at B. That's all they are trying to say, but the current is increasing. So the moment the current passes through this inductor, which is a loop of wire, the moment the current passes through it, the current is increasing. So if it is increasing, there's actually changing magnetic flux. And this magnetic flux tends to oppose the This magnetic flux tends to oppose the change in magnetic field or magnetic flux that is generating the EMF itself. So here we are going to get the potential at A, which is the VA, the VAB, to be greater than 0 because there is increase in current that is passing through. For that matter, an EMF will be induced. This EMF that will be induced, note that this EMF that will be induced will act as a temporal source of EMF. So at the end of the day, when there is an EMF that has been removed from the circuit, you are still going to get some current that will be moving through for a specific time, usually a shorter period of time, because it acts as a temporal source of EMF in the circuit whenever there is a disconnection of this main source of EMF. So according to Lenz's law, so this will be the direction of the EMF. As the current is moving this way and the current is increasing, the EMF that will be induced will be opposing the direction of the current that is providing the EMF. So according to Lenz's law, the EMF induced by the current through the loop will act in opposite direction to the flow of current if only the current is increasing. That's what you should keep in mind. If only the current is increasing, we are going to get your EMF be acting in opposite direction to the current. Now let's move on to the point D. The point D is when the current is decreasing. So if the current is decreasing, obviously the potential at A will be will be lesser than the potential at B. So VAB will be equal to the length times the I over dt, which is less than 0. If it is less than 0, then it means that you are going to get something in negative. Okay, so the EMF, so if the current is decreasing through the solenoid or the inductor, then the EMF that will be produced, this EMF will be acting in the same direction with the current. Okay, the first one was increasing and the EMF was opposite. This one, the current will be moving in the same direction with the EMF because it is decreasing. So that's the fact that you should know. So here the EMF will act in the same direction as the current to maintain a steady current temporarily. Okay, so the moment the current moving through the solenoid is decreased and there's a disconnection of the main source of EMF, this EMF will act in the same direction with the current. So at the end of the day, you as an observer looking at the appliance or the circuit, the moment the EMF is disconnected, or the moment the main EMF source is disconnected, you are not going to see the change drastically. You are going to see it decreasing gradually. Okay, the moment the EMF is disconnected, or the moment the main EMF source is removed from the circuit, this EMF that has been induced will act as as a steady current temporarily before at some point in time it goes off. So now let's talk about Lenz's law. When you bring a magnet into a loop of wire, what happens to it, and what happens to the magnetic flux, and also what will be the direction of the magnetic field. So if this is your bar magnet, the north pole is rather facing the loop. If you tend to bring the magnet into the loop, there's one thing you should know. If you tend to bring the magnet into the loop, you have to assume, the best way you can solve problems like this is that you have to assume that there is also another magnet that will be opposing it, so that this magnet will not enter the loop directly. Okay, what I'm trying to say is, there is a magnet, the north pole is rather facing the loop. So this is that you have to provide an imaginary magnet which will prevent this magnet from falling directly into the loop. So here there should be a magnet with a north pole, and this north pole, what is this north pole going to do with this magnet? It's going to repel, because laws of attraction means like pairs repel, like charges repel, or like poles repel, unlike poles attract. So if there's a north and there's a north, what they are trying to say is that this north pole will repel this magnet, and it will in turn keep it from entering the loop directly. That's what I'm trying to say. So from here, this is your imaginary magnet. When you take a magnet, for instance, we all know that the magnetic field lines, it moves from the south to the north. Sorry, it moves from the north to the south. So when you're having something like this, for this imaginary magnet, this is the direction of the magnetic field lines. The direction of the magnetic field lines are moving out, okay, to the south. So using your hand rule, this is how you are going to do it. You are going to curl your hand this way. Using your hand rule, you are going to curl your hand up into the coil. You are going to curl your hand into the coil. Okay, so when you curl your hand into the coil, this is the direction of your thumb. So your thumb will be moving this direction. And when you are having a direction like this, it is counterclockwise. Okay, when you're having a direction like this, it is counterclockwise. Now let's move to this second scenario. When you are having your north pole and your south pole, and in this diagram we are seeing that your magnet is moving out of the loop. So what should be done so that this magnet will not move out of the loop, but it's rather be maintained at the same position? You have to bring an imaginary magnet which will in turn act as an attracting agent, which will attract this force. And when it attracts this magnet, it is going to keep the magnet in a steady form. So you have to bring a magnet which is having a south pole, and this south pole will attract the north pole here. Okay, and we all know that for a south pole, electric field lines move into the south from the north. Okay, so when you are using your hand rule, for instance, you are going to curl your hand into the coil. So when you curl your hand into the coil, this is the direction of the current. Okay, so when you curl your hand, this will be the direction, and this direction is clockwise. That's what I'm trying to say. So the same thing also applies to the third example here. So for the third example here, we are having a magnet with a south pole that is moving into it. So this is that you have to bring an imaginary magnet which is having a like pole, which will repel it from moving into the coil directly. and here we bring what? A south pole. So when we bring a south pole, for instance, it's going to what? Repel it. And if it repels it, it's not going to what? Allow the magnet to fall into the loop. And when you bring a south pole, magnetic field lines moves into the south pole. So this will be the direction into the coil. This will be the direction. Okay. So your hand will actually be facing this way, and this direction is what's called what? The clockwise direction. Now let's look at this last example for instance. The same magnetic what? The same magnet, but this time around the magnet is moving out of the loop. It's moving away from the loop. So what should you do so that what is going to attract this magnet? You have to bring an imaginary magnet, which is what? Having a north pole. So this north pole will what? Attract the south pole in a way that it's not going to allow this magnet to move up completely. Okay, so it's going to keep it there. And when you are having a north pole, the electric field lines moves out of it. So these are what? The magnetic field lines are moving out of the what? Of the loop or the coil. So now we are going to curl your hand this way. And when you curl your hand this way, it means that the current is what? Moving out of the what? The current is moving out of the what? Of the loop. So when you curl your hand this way, this will be the direction of the what? Of your finger. So now this direction is called what? The clockwise direction. Now there are some qualitative questions that you need to know about what? About the magnetism. Let's look at this one for instance. Let's say we are having a magnet. Okay, we are having a magnet with a north pole, and this magnet with a north pole. Let's assume that we are having what? A beam of electrons, which is a negative charge. Okay, and this negative charge is coming towards you. Okay, and you are saying that you put a north pole of magnet directly above the beam. Okay, so the magnetic field, which is B, that I've indicated here, is straight down or points straight down. That's what I'm trying to say. So these questions like this, it means that you are going to apply your right hand rule or your left hand. Here, depending on the charge is negative, which is electron. So you are going to use your left hand. So if you are using your left hand, means that we are going to apply the left hand rule. So this is your direction of the what? This is the direction of the magnetic what? Field. And they are saying that the velocity is pointing towards you. Okay, which is the Z direction. And this, your magnetic or field lines, which is your fingers. We represent the magnetic field lines as your fingers. And represent the what? We represent your thumb as the what? As the velocity. So the velocity is actually pointing towards you. Then from there they are asking you that what? Which way would the electron what? Beam deflect? So based on the direction of the force, you know where the electron will be deflecting to, because it is the force that will be providing the motion of the electron. Okay, so if you are able to detect the direction of the force, then literally you are going to know what? The direction of the electron, where it's going to deflect to. So when you use your left hand rule, the thing is facing you this way. But here you are not going to use your right hand. This is my right hand, so you are going to use your left hand. So if you are using this left hand, this is the direction of the electron. Okay, and this is your direction of the electric field lines, which is your fingers. So now, per our left hand rule, we are going towards the direction of our palm will indicate the direction of the force. So the direction of the force, we're pointing to my left. Okay, so at the end of the day, the force is pointing to the left, and it's the force that is causing the electron beam or the electrons to also deflect. So if the force is deflecting to the left, then automatically your electron will also will be moving to the left, or it will be deflecting to the left. Okay, so they said note, the force always causes the electrons deflection. Hence, wherever the force is directed, that's the direction of the electron. So that's all what you should know about it. Now let's move on to dipoles. When we are talking about dipoles, for instance, you are having when you're having a dipole, here you are talking about electric charges. This is the direction of your electric field, and this is your dipole. Dipole means there are two charges, just that they are having the same magnitude but opposite direction. One is negative, the other one is positive. They are all having the same magnet. They are all having the same magnitude. So from here, this is the direction of the electric field. You should always keep in mind that when the electric field lines and the dipole, if they are parallel or if they are in the same plane, there is not going to be deflection, because at the end of the day, one force will be pulling it here. At the end of the day, for instance, one force will be pulling it here. The other force will also be pulling it here. So they will cancel out. Okay, so there will be no torque, or there will be no rotatory movement. But looking at this diagram, for instance, this is the direction of the electric field, and this is the direction of your dipole. So you could see straight forward that there is going to be some force that will be causing it to So at the end of the day, you could see that there will be a force that will be causing it to rotate. Okay. So the same thing applies. If you are seeing something like this, this is the dipole, this is the direction of your dipole. Okay, this is the direction of your dipole. And now they are telling you that this is the direction of the electric field. Okay. So this means that there will be a force that will cause it to move this way. Another force also causes it to move this way. So at the end of the day, the thing will be rotating. Okay, so as it continues to rotate, then there will be a torque. So when you are finding for a torque, this is the distance of separation between the two charges. Okay, so this is the length of it, capital L. At the midpoint of the distance, let's represent it as small d. Okay, so when you are finding for torque is simply the force times half of the distance. So F times d. Okay, and d is literally d is equal to L over 2. That is half of the length of half of the full length. That is d. Okay, so when you are finding for torque is equal to force times distance. So there will be a rotatory force here, which is torque 1. This torque 1 is defined by this force 1 times small d. So our torque 1 is equal to F1 times d. The same thing applies to torque 2. Torque 2 is the same thing as F2 times d. But I've stated it earlier that our L is equal to our d is equal to L over 2. So if our d is equal to, like how I've stated earlier that our d is equal to L over 2, then wherever we see d, we put L over 2 there. So at the end of the day, we are going to get force times L over 2 plus force times L over 2. When you add these two, you are going to get force times the length. So when they ask you to find the net torque, just know the length between the two charges times times one of the force. Okay, because at the end of the day, the forces are the same. So times one of the force. Now let's look at something here. Whenever you are having your dipole, which is parallel to the electric field, this is your electric field. Okay, this is your electric field. So whenever you are having your dipole, which is parallel to the electric field, then you are not going to get any motion, because at the end of the day, one force will be pointing here, at the end another force will be pointing here, and these two forces have the same magnitude, just that they are opposite in direction. So F2 minus F1 will give you 0. But when you are having something like this is that there will be a force that will be rotating it here, another force will be rotating it to this direction. That's what I'm trying to say. At the end of the day, they'll be moving in a circular motion, producing a torque. Okay, these forces are the ones that will be producing a torque. So when they ask you to find a torque of, let's say, the positive charge, then that torque will be equal to F1 times half of the distance between the two separations, or between the two charges. So at the end of the day, we are going to get torque, or we are going to get a non-zero number. But let's look at this one for example. This is the direction of the electric field. Okay, this is the direction of the electric field. one force will produce here, the other force will produce here. So you could see that what the torque that will be produced here will be maximum as compared to this one, because there's a general what formula for torque, and the general formula for torque is what? Q times E, and the Q times E is just a force. Okay, force is equal to what? QE. From our previous lessons about electric field, force is equal to QE. So you can substitute it here, sine the theta. So F sine theta, that is the angle of the what? Of the force. Okay, so for this particular one, the angle is actually the angle between the what? The force and the electric field. For this one, if this is the direction of the what? If this is the direction of the electric field, then the force will be producing it in the what? In the opposite direction. Okay, so at the end of the day, they are forming a 90 degrees. So for this particular diagram, we are having what? 90 degrees what? Angle, and sine 90 is what? 1. Okay, so at the end of the day, when the dipoles are perpendicular to the what? To the electric field, then, or when the dipole moment is perpendicular to the what? To the electric field, they are going to get what? A maximum what? A maximum torque. But when the dipole moment is parallel to the electric field, they are going to get what? Sine 0, and sine 0 is 1, because if they are parallel, the angle between them is what? 0. And that's what I'm trying to say. So our torque will be equal to what? QE sine 0. Sine 0 is what? 0. 0 multiplied by QE will give you what? 0. So this one will give you the minimum, and this one will give you the maximum, and this one will give you a value that is what? Intermediate between the two. That's what I'm trying to say. So in my next video, I'll be discussing more about the what? About how to apply the formulas. Since there are some of the formulas, they may represent it as what? Rho or something like this, but how will you know that this is the meaning of what they are trying to say? How will you know that this is what? Electric field density or electric charge or magnetic flux? You will not know. So in my next video, I'll be discussing more about it, or I'll be including it in this video. So stay tuned.